So let's say if you have a ball and the ball is moving to the right and there's a force that's acting on the ball and it's parallel to the velocity vector. What's going to happen to the ball? If the force and velocity vectors are parallel, the ball is going to speed up. Now, what if the force and the velocity vectors are anti-parallel? If they're opposite to each other, what's going to happen to the speed? The ball is going to slow down. Now, what about if the velocity vector is perpendicular to the force vector? What happens? If these two are perpendicular, then the ball is going to turn at constant speed. It's going to change direction. This force is known as a centripetal force, provided that that force remains perpendicular to the velocity vector. If that happens, then we have uniform circular motion. Now, the centripetal force is not really a new kind of force. Rather, it's created by another force. So let's say if you have a ball attached to a rope, and you're swinging this ball in a horizontal circle. What provides the centripetal force? In this problem, you provide the centripetal force. And that force is transmitted through the rope, which is known as a tension force. So in a horizontal circle, the tension force provides the centripetal force in this example. Now, what about when the sun orbits the Earth? The Earth orbits the sun, rather. What provides the centripetal force in this case? Because we have circular motion in this example. So what keeps the Earth in orbit around the sun? In this case, it's gravity. Gravity provides the centripetal force. Gravity pulls the Earth towards the sun, but the Earth wants to fly outward towards outer space. So instead, it turns. So gravity keeps the Earth in orbit around the sun. So as you can see, the centripetal force is not really a new kind of force. It's a force that's provided by another kind of force. So any force that causes an object to move in a circle can be labeled as a centripetal force. So another example is, let's say if you have a car turning. In this case, the static frictional force provides the centripetal force. It allows the car to make that turn on a road. Another example that you won't see in this video, but you'll learn more about it in the next semester of physics, is the magnetic force. Let's say if you have a proton or any positive charge, and this positive charge is moving towards the right, and the magnetic field, let's say it's going into the page. In physics 2, you'll see it's represented by an X symbol. A dot means out of the page. So the magnetic field is going into the page, and this charge is moving towards the right. It's going to feel a magnetic force that's going to cause the proton or the positive charge to turn. And so whenever you have a moving charge in a magnetic field, that charge is going to turn. It feels a magnetic force exerted on it by the magnetic field. And so this magnetic force can behave as a centripetal force because it's causing the object to turn. So those are the main 4 examples that you'll see in physics. In the case of a rope, tension can provide the centripetal force if an object is moving in a circle. In the case of planets, it's gravity. In the case of a car turning, it's static friction. And if you have a moving charge in a magnetic field, it's going to be the magnetic force that provides the centripetal force. So how can we find the equation of the centripetal force? Now, according to Newton's second law, the net force is equal to the mass times the acceleration. So the centripetal force is mass times the centripetal acceleration. And the centripetal acceleration is v squared over r. So the centripetal force is mv squared over r. It's directly proportional to the mass, and it's proportional to the square of the speed. And it's inversely related to the radius of the circle. Now, there are some other things that you need to know about this equation. For instance, whenever the mass increases, you need to know that the centripetal force will increase as well. If the speed increases, the centripetal force will increase. And if you increase the radius of the circle, the centripetal force will decrease. So imagine if you're driving a car, and if you make a sharp turn, you're going to experience a very large centripetal force. You're going to feel like you're flying out of the window. If you decrease the radius, the centripetal force will increase. But if you make a wider turn, you won't feel like you're flying out of the window as much, because the centripetal force is a lot less if you increase the radius of curvature. Now, if you try to make a wide turn at a very high speed, you're going to feel a much larger centripetal force. And if you make a sharp turn with a very high speed, you might actually fly out the window. So that feeling that you get when you make a turn, you can increase it or decrease it. So if you want to decrease that feeling when you're turning, just decrease the speed and increase the radius of the turn. And you won't feel that centripetal force effect as you would when you make that turn. So just make a wider turn at a slower speed. Now, if you want to fly out the window, drive fast and make a sharp turn. I would not recommend that, though. Now, here's a question for you. If you double the mass, what effect will that have on the centripetal force? If you double the mass, the centripetal force will double. If you triple the mass, the centripetal force will triple. To answer questions like that, just plug it into the formula. Everything else that doesn't change, replace it with a 1, so you're going to get 3. Likewise, if you double the speed and keep everything constant, the centripetal force will increase by a factor of 4. Now, what if you double the radius of the circle? What's going to happen? The centripetal force will be 1/2 of its original value. And if you reduce the radius to 1/2, the centripetal force will be 1 over 1/2, which is 2. It's going to double. Now, what if you triple the mass, double the speed, and decrease the radius by a factor of 3? What effect will that have on the centripetal force? So if you triple the mass, double the speed, and reduce the radius to 1/3 of its value, 2 squared is 4. And 3 times 4 is 12. 12 divided by 1/3 is the same as 12 times 3, so it's 36. The centripetal force will increase by a factor of 36. Now, let me give you another example. Let's say if you quadruple the mass, triple the speed, and reduce the radius to 1/4 of its value. Go ahead and find the effect that it will have on the centripetal force. So we quadruple the mass, triple the speed, and the radius is 1/4. So it's 4 times 3 squared. 3 squared is 9. And 4 divided by 1/4, that's like 4 times 4, that's 16. So we got 16 times 9. 10 times 9 is 90. 6 times 9 is 54. So this adds up to 144. So if you quadruple the mass, triple the speed, and reduce the radius to 1/4 of its value, the centripetal force will be 144 times greater than its current value. Now let's move on to some practice problems. A 0.25 kilogram ball moves in a horizontal circle of radius 1.5 meters at a speed of 30 meters per second. What is the centripetal force acting on the ball? So here's the ball. It's moving in a circle. the centripetal force is always directed towards the center of the circle, and it's equal to mv squared divided by r. So we have everything that we need. We have the mass of the ball, which is 0.25 kilograms, and we have the speed, which is 30 meters per second, and the radius is 1.5. 30 squared is 900, and 900 times 0.25 is 225. If you divide that by 1.5, you're going to get 150. So that's the centripetal force acting on this ball. It's 150 newtons. Now let's move on to this example. A 500 kilogram car makes a circular turn at a speed of 12 meters per second. If the centripetal force acted on the car is 9,600 newtons, what is the radius of the circular turn? So we have the mass, which is 500 kilograms. We have the speed, which is 12 meters per second. And we have the centripetal force, which is 9,600 newtons. All we need to find is r, the radius. So let's start with this equation, and let's rearrange it to get r. So I'm going to multiply both sides by r. And so these will cancel. So I have the centripetal force times the radius is equal to mv squared. Next, I'm going to divide both sides by the centripetal force. So the radius of the circle is going to be the mass times the square of the speed divided by the centripetal force. So this is the formula that we need for this problem. So let's go ahead and get the answer. So it's going to be the mass, which is 500 kilograms, multiplied by a speed of 12 meters per second squared, divided by the centripetal force of 9,600 newtons. Twelve squared times 500 is 72,000. And if you divide that by 9,600, you're going to get a radius of 7.5 meters. And that's it for this problem. A 0.35 kilogram ball is attached to a rope moving in a horizontal circle of radius 85 centimeters. If the rope can withstand a maximum tension force of 1,500 newtons, what is the maximum speed that the ball can travel in this circle without breaking the rope? So in this problem, we need to calculate v, the maximum speed. So let's solve for v in this formula. So what I'm going to do is I'm going to multiply both sides by r over m. Now the reason why I'm doing that is to cancel the radius on the right side and also to cancel the mass. So all I have left over on the right side of the equation is v. So now I need to take the square root of both sides. So v is equal to the radius times the centripetal force divided by the mass with a square root symbol. So now let's plug in everything that we have into this formula. The radius is 85 centimeters, and we need to convert that to meters. 1 meter is 100 centimeters. So to convert it, take 85 divided by 100, and that will give you 0.85 meters. The centripetal force is going to be the maximum tension force, which is 1,500 newtons. Whenever you have an object moving in a horizontal circle, and if it's attached to a rope, the tension force is approximately equal to the centripetal force if the ball is moving fast enough. If not, you're going to have what is known as a tetherball experiment, and it's not going to be the same. But if it's moving fast enough, you don't have to worry about the weight force of the ball. It's going to be insignificant. But I'm going to go into more detail into that topic in another video. Right now, let's plug in the mass, which is 0.35. 0.85 times 1500, that's 1275. And if you divide that by 0.35, you should get like 3643 if you round it to nearest whole number. And then take the square root of that number. And then the maximum speed is going to be 60.4 meters per second. So now you know how to calculate it if needed. But now let's go over some free body diagrams. Now imagine if you're holding a rope in your hand that's attached to a ball. And if you spin it fast enough in a horizontal circle, it's going to look something like this. If it's going fast enough, it's going to appear nearly horizontal. If it's not going fast enough, it might be slightly at an angle. And if it's going slow, the angle is going to be larger. So it's going to look like this. Now, the tension force is the force in the rope. So that's going to be the tension force. That tension force has an X component and a Y component, which I'm going to call FTX and FTY. Now the ball also has a weight force, mg. So this if it's moving relatively slow. This angle is going to be significant. Now, the centripetal force is the force that's going to keep it moving in a circle. So it's the horizontal component of the tension force. So when a ball is moving slow, FTX is equal to the centripetal force. This is always true, but I'll talk more about when it's moving fast. FTY is equal to the weight force. This component balances the weight force. Now, if you want to find a tension force, it's going to be the square root of FTX squared plus FTY squared. To find FTX, you need to find the centripetal force, which is mv squared over r. And then FTY is mg. So if you want to get the exact answer for the tension force, here's the equation you need to use. FTX is mg, right? No, I take that back. FTX is mv squared over r. So you have mv squared over r squared plus FTY squared, which is mg squared. So for any situation, this will be the exact answer for the tension force. Now, if the ball is moving fast enough, it's going to look like this. Now, we can't really see anything, so I'm going to use this picture. This is still going to be FT, and you're still going to have FTX and FTY. But when it's nearly horizontal, FT is approximately equal to FTX. FTY will be negligible. So if the ball is moving fast, you could say that FT is approximately FTX, which is the centripetal force. So that's going to be mv squared over r. This part becomes insignificant. Now let's use this equation to see if we can get the same answer. So I'm going to square both sides. So I'm going to have ft squared is equal to mv squared over r squared plus mg squared. So the tension force is 1500. The mass is 0.35. We don't have the value of v. R is going to be 0.85. And this is squared. And then we have mg squared, so that's 0.35 times 9.8 squared. Now 1500 squared, that's a big number. That's 2,250,000. 0.35 divided by 0.85, that's 0.411. Well, let me square it too, so I could just make this a lot easier. It's like 0.41176 and then it repeats. Once you square it, you're going to get 0.16955. And then v squared squared, that's going to be v to the fourth power. 0.35 times 9.8, that's 3.43. And then once you square it, it's 11.7649. Now, if you take this big number and subtract it by that small number, it's going to be insignificant, but we'll do it anyway. So let's subtract both sides by 11.7649. So this is going to be about 2,249,988.235. So now let's divide both sides by 0.16955. So you should have 1327035.2.32 is equal to v to the fourth. So now I'm going to raise both sides to the 1/4 power to get v. So take the fourth root of both sides, and this will give you 60.356, which rounds to 60.4 meters per second. So as you can see, the answer doesn't change much. If the ball is moving pretty fast, and if the mass is small, then we could say that the tension force is approximately equal to the centripetal force, so it's going to be mv squared over r, if it's a horizontal circle. So if you have an object that looks like this, if it's moving in a horizontal circle, then the tension force is just mv squared over r, if it's moving fast enough. If it's not, if it's at an angle, then it's different. Then you need to use this equation. It's going to be the square root of mv squared over r squared plus mg squared, if it's at an angle. But that will give you the exact answer. It's just a lot more work. Here's the last problem. Asteroid X orbits moon XYZ with a speed of 500 meters per second and a centripetal force of 1500 newtons. And asteroids X, Y, and Z all have the same mass. Now, if asteroid Y orbits the same moon with the same orbital radius as asteroid X, but at a speed of 1000 meters per second, what is the centripetal force acting on asteroid Y? So let's say this is a moon that's orbiting some planet. And then we have an asteroid orbiting that moon. So this is asteroid X. Now, asteroid Y is in the same orbital radius as X. Now, X is moving at 500 meters per second currently. And asteroid Y is moving at twice the speed, 1000 meters per second. Now let's go ahead and put asteroid Z in part B. Asteroid Z is at half of the orbital radius relative to X. So somewhere here, we're going to have asteroid Z. And it's going at 1500 meters per second. Now the centripetal force on X is 1500 newtons. What is the centripetal force acting on Y? How can we find the answer? Well, we can't use this equation directly. We have to use it indirectly. Now, if we focus on X and Y, everything is the same. They have the same mass and the same orbital radius. The only thing that's different is the speed. Now, what happens to the centripetal force if the speed is doubled? So the mass doesn't change. Let's put a 1. The speed doubles, and the radius doesn't change. 2 squared is 4. So the centripetal force will increase by a factor of 4 if we double the speed. So if x has a centripetal force of 1500, then y is going to be 1500 times 4. So the centripetal force is going to be 6,000 newtons. Now, if you want to come up with an equation that relates centripetal force to speed, given that everything else stays the same, like the mass and the radius, here's the formula that you could use. So we're going to say F2 over F1, where these two represents the centripetal force of two different objects. That's going to be m v2 squared over r divided by m v1 squared over r. Now, I didn't use any subscripts for m and r because they're the same. So therefore, they're going to cancel. So F2 over F1 is equal to V2 squared over V1 squared. This is the formula that you want to use. Now, if you want to solve for F2, multiply both sides by F1. So F2 is going to be F1 times V2 squared over V1 squared. Or you could just write it like this if you want. V2 over V1 and then square it. So let's use that formula. So F1, where 1 is the first object, asteroid X, is 1500. The speed of asteroid X is 500. And the speed of asteroid Y is 1000. So 1000 divided by 500 is 2. And 2 squared is 4. 4 times 1500 is 6000. So this is the formula that you could use if you need to relate the centripetal force with the speed together. Now let's move on to the next part. Part B. If asteroid Z orbits moon XYZ with a speed of 1500 meters per second, but an orbital radius that is half of asteroid X, what is the centripetal force acting on asteroid Z? So let's think about it conceptually. The speed relative to X increases by a factor of 3. It goes from 500 to 1500, and the radius is 1/2 of its value. So what happens to the centripetal force if we triple the speed and cut the radius in half? So let's use the equation. The mass doesn't change, so we're going to replace it with a 1. The speed triples, so let's put a 3. And the radius is reduced to 1/2 of its value. 3 squared is 9. 9 divided by a half, or 9 times 2, that's 18. So the centripetal force will be 18 times its value. So it's going to be this number, 1500 times 18. So asteroid Z is going to have a centripetal force of 27,000 newtons. Now let's confirm this answer with an equation. So I'm going to use F2 over F1 again, which is equal to m v2 squared over r2 divided by m v1 squared over r1. So the only thing that's the same in this example is the mass. That's the only thing I can cancel. Now, using the keep, change, flip principle, if you keep this the same, change division to multiplication, and flip this fraction, you're going to get this expression. It's going to be v2 squared times r1 over v1 squared times r2. And then let's multiply both sides by f1. So f2 is going to be f1 times r1 over r2 times v2 over v1 squared. So now let's plug in the values that we have. So F1, that's the original force for asteroid X, that's 1500. R1, we don't have a value, so we're just going to plug in 1. R2 is half of R1, so it's 1/2. Or you could say if R1 had a radius of 2, R2 is going to have a radius of 1. If R1 has a radius of 4, R2 is going to have a radius of 2. Either case, the ratio of R1 to R2 is going to be 2. V2 is 1500. V1 is 500. And then that's squared. So we have 1500 times 2, and then 1500 over 500 is 3. 3 squared is 9. And 2 times 9 is 18. So then we have 1500 times 18, which is going to be 27,000 newtons. So that's how you can get the answer. Now let's see if all of this makes sense. So asteroid X is moving slow, and it's making a wide turn. So therefore, the centripetal force is very small. Asteroid Y makes the wide turn like X, but it's moving faster. So it has a much larger centripetal force. Asteroid Z makes a sharper turn, and it's moving very fast. So it has an extremely high centripetal force. So make sure you understand this concept. So if you're in a car, and if you make a wide turn driving slow, the centripetal force that you're going to feel is very, very low. You may not even feel it at all. Now, if you make a sharp turn going very fast, you're going to feel it. And the faster you go and the sharper the turn is, the more you're going to feel. So just make sure you understand that. And that's it for this video. Hopefully it gives you a good understanding of centripetal force and how to solve problems associated with it. So thanks for watching.